Hey everybody, welcome back to Module 5. In this module, we extend just by one step what we've been talking about the past 4 modules by talking about what are called random slope models, which are very cool, very useful extensions to multi-level modeling. So before I get into the details of random slope models, I noticed over the past couple weeks on the discussion boards, a lot of folks are asking some version of this question. How do I write up the results of an MLM analysis? Do I need to include an equation? How much detail? How do I interpret things? What does it look like in the published research? So on and so forth. I highly recommend finding an article in your field that uses multi-level modeling. And that might mean going to a journal that publishes things that you're interested in and just searching for the term multi-level modeling. It's also known as HLM, hierarchical linear modeling, in some places, so you could search for that term as well. But I also have a few resources that might help. So in your textbook, Appendix 2 in Garson is just about writing up multi-level results. That's actually what it's called. It's a list of things you need to include, and it provides some examples. And it was written with one of Dave's doctoral students, I believe, or colleagues who does a lot of this work. So that's a really good place to start. Another good place to look, and I've included the link here, is a chapter by Betsy McCoach, who is a methodologist at UConn, in what's called the Reviewer's Guide to Quantitative Methods in the Social Sciences. Now, this is a really cool book. If you haven't seen it before, I highly recommend you check it out. We actually have the new updated version of this book, which came out last year, and that's actually where this chapter is. I should say that 2010 was the old edition. I think it's 2019 now. We have this in our VCU library online, and you can download all the chapters, so it's very accessible. This is such a cool book. It's designed for people who review quantitative papers, and it just basically gives you a nice overview of the method and tells you everything that you should be looking for as a reviewer in each section, which is pretty cool. It's edited by Greg Hancock, who is a friend of us here at VCU, and some colleagues at Maryland, and it's an invaluable resource. I use it all the time. It goes into way more than just multi-level modeling. But anyway, the chapter by McCoach is a great example of what reporting on this stuff should look like. What are the things you want to include? And there's a nice link there if you're interested in that. And then finally, I'm including an example of mine, specifically an example of a growth model. Multi-level growth model, and this is from research that was done right here at VCU with a colleague of mine who has moved on to a different institution, as well as some of our RAE students, which is pretty cool in our little track. So that's another example, and in that paper we use growth models, which we will get to I think maybe module 7 or 8, so it's coming up. We will study growth models. So those are another really cool application of MLM. So if you're interested, 3 great resources for getting a better sense of what it means to write stuff up in this framework. Okay, let's dig into random slope models. So last week, we learned how to run and interpret what are called random intercept models. And we also learned how to introduce predictors into our regression models at level 1 and level 2. Hopefully that seemed fairly straightforward to you. It looked like it was going pretty well based on the discussion board. Predictors can be added at level 1 or level 2. So if we're talking about students in schools, predictors can be included at the student level and at the school level. And their interpretation is pretty straightforward. It's very similar to regular regression. A 1-unit change in X, whatever that means, your IV predicts a beta unit change in Y, controlling for all other predictors in the model and the level 2 random effect. So controlling for what school you're in, essentially. if the example is students nested in schools. We can even explore moderators. So we dipped our toe into the lake of moderator analysis a couple weeks ago, and I put together a page that went a little bit deeper into moderator analysis and interaction effects. I think that was in Module 3 maybe, or maybe Module 2. And we're going to continue that work this week by talking about cross-level interactions, where we're actually interacting a level 2 predictor with a level 1 predictor, which is a really cool extension on moderator analysis. So that's all stuff we've done so far. So the whole idea of this course is that we're building gradually. We start with something that you know, which is simple linear regression, and we just start adding components. And before you know it, we're doing some pretty cool, sophisticated multi-level models that are able to answer all sorts of different research questions. So this week, we're going to go a step further. Last week was random intercept models, and we're going to talk about how to incorporate random slopes, how to add them in, how to interpret them, and also how to test for whether or not we need them or not. So very similarly to a random intercept, what a random slope does is it allows a little bit of variability for a given predictor across schools or whatever our higher level clustering variable is. So remember, just think about like a random intercept. With a random intercept, it allows that average score, whatever that is, to vary according to what school you're in, which was super useful. Well, a random slope does the same thing, except it allows the direction of the predictor, the actual slope estimates themselves, to vary slightly according to what context you're in. So not only are the intercepts changing, but it allows the slopes to change based on what context you're in, which is super cool. So you can model that variation according to each cluster, and each cluster gets its own unique value under a random slope model, which is really, really neat. This is much more flexible than our typical assumptions that we would get in, for example, regular regression, where in regular regression, we assume the intercept holds for everyone, and we assume all the slopes hold for everyone equally, regardless of context. And this really relaxes those assumptions and lets us explore variability in really cool ways. Okay, so now for a little art project that I put together that hopefully is a little bit more helpful. I want to convey what this means, this idea of random slopes and random intercepts. Okay, so prior to this week, we have been studying what are called random intercept models. And they're the first step in sort of understanding MLM. So here is a very basic psych example. Let's say we have a measure of achievement. That can be anything. And we have a measure of self-efficacy. Again, it could be specific to a content area, regardless. We're going to assume that both of these things are relatively continuous, right? So these are continuous measures. So what we find, so here's our overall model. We essentially find a positive relationship between self-efficacy and achievement. Makes sense. And here's our intercept, which is the average score of achievement score for a student who has a self-efficacy score of 0. So we have that there. Okay, so if we were doing regular regression, all we would get is this line right here, this thick line. When you introduce a random intercept model, suddenly it allows that line to vary and move up and down the y-axis. So school A, if I'm a student in school A, I might have a higher intercept. If I'm in school C, I might have a lower intercept. School B, so on and so forth. So when we talk about random intercept, we mean that there's a little bit of variability in that starting point depending on what your context is. Okay, so that's a random intercept model. Now, from here, we're talking about not only a random intercept, but also random slopes. And so this is kind of an exaggerated example. Sometimes the slopes don't get this different. But in this example, again, we have our overall model, which is right here. the same line, and it's positive. So students with higher levels of self-efficacy are predicted to achieve more. But depending on what school you're in, the slope of that line can look radically different. So here in school A and school B, that line is positive. So it sort of confirms the overall model, right? So although the slope is more extreme in some cases than in the overall. But look here, so in school C and school D, and again, I apologize for my chicken scratch. It's not the nicest looking graph. These schools actually have negative slopes. So the more self-efficacy a child has is actually associated with lower achievement. Now that's kind of crazy. It's hard to understand why that would be in a particular school, but I kind of exaggerated this example just to show you this is the kind of variability that you can find when you introduce both random intercepts and random slopes, and it allows you to ask lots of really interesting questions. So hopefully that helps a little bit. Okay, so returning to Garson's example here, I really like his diagram and how he sort of lays out these concepts. So this week, we are again going to be talking about running a null model, which is arrow 1, and a conditional random intercept model, which includes arrow 2 and arrow 4. So arrow 2 is just the relationship between the level 1 predictors in your outcome, and arrow 4 is the relationship between level 2 predictors in your outcome. Again, these things are fixed in a random intercept model. The values of the predictors are fixed. The same, the student, regardless of what context the student is in, those estimates hold. Now, we're going to get a little bit crazier. So this week, we're going to add a random slope model. So that incorporates arrow 4 here. So that is the case where the school you're in changes the slope of a level 1 covariate. So it allows it to vary. Think about those lines going from being perfectly parallel to kind of all over the place. That's what we're adding this week is arrow 3 that is connecting the school to the slope. We're also, in the examples, I'm also going to demonstrate a cross-level interaction model. And cross-level interactions actually capture all 5 of these. So in that model, we're going to incorporate all 5 different types of effects. In one, a little bit of a bonus, which is really cool. But for now, we're just going to focus on 1, 2, and 3. Okay, so now we're going to talk a little bit about notation. Brace yourself. I know you can do it. We're going to dig in here and think about this just a little bit. So this is the notation for a null multi-level model. So this is a refresher. So here we have an outcome, Yij, which is a score for student I in cluster J. And that is equal to some intercept, beta 0j, plus some student-specific random error term, okay? And then beta 0j can be split out even further into some overall intercept, which we're calling gamma 00, plus a random component at the school level, which we're calling mu 0j. So now we actually, in a null model, in a random intercept model, we have 2 random components. We have a random component at the student level, which is epsilon ij, and then we have a component at the school level, which is mu 0j. And both of these are assumed to be normally distributed with a mean of 0 and a specific variance. And again, the variance, this is how we calculate an ICC. We figure out how much of the variability is in tau 00 relative to the rest of the variability that's unexplained, which is in epsilon. Okay, so that's the null model. Last week, we talked about how to add predictors. And I basically showed you, so here we have level 1 predictors now. It's no longer a null model. So we have predictor 1, x1, predictor x2, and predictor x3. And then we get betas. So we get a beta estimate for predictor 1, we get a beta estimate for predictor 2, and predictor 3. And these measures vary at the student level. So this is predictor 1 for student I nested in school J, predictor 2, and predictor 3. So this might be a prior score, a pretest score. These might be demographic or background covariates. These might be other types of predictors of interest, okay? We can also add level 2 predictors. And in this case, W represents a level 2 predictor. So maybe that is a measure of school funding or school characteristics or urbanicity or a averaged measure of a group 1 or level 1 predictor. It could be any of those different things. And the coefficient for a level 2 predictor is called a gamma. So gamma 0, 0 is the average, and then gamma 0, 1 is the estimate of the slope for that predictor. We still only have 2 random components, epsilon ij and mu 0j down here at the bottom. So in other words, beta 1, beta 2, and beta 3 are what we call fixed. So regardless of what cluster you're in, you would be assumed to have the same value for that predictor, not for that variable, right? That variable can vary, but the impact of that variable, its association with the outcome, is assumed to be the same. Okay, so now we get a little bit fancier. So we go from a random intercept model where we only have mu 0j. Let's talk about incorporating a random slope. Okay, so the model is almost identical to what we had before, except, so let's say I want predictor x here to have a random slope. Now that estimate for x is composed of some average value for that slope, and we call that gamma 1, 0, plus some random variability at the class or school level, whatever your higher level clustering variable is, and we call that mu 1j. So in other words, we've introduced a second random component at the school level. Mu 0j up here is the component that allows the intercept to vary. Mu 1j is the component that allows the slope of x1 to vary based on what school you're in. So pretty cool concept, actually, right? So we'd actually could do this for all of the predictors. We've only done it for beta 1 here, just as a trial. And I get to some notes about how many predictors you want to think about adding a little bit further below. So here's the tricky part. Technically, we have now introduced random components, random variables, 2 of them at the same level. And so really, if we're sort of following the rules of linear algebra and matrix algebra, we should allow these 2 random things to co-vary with each other. All right, so otherwise we're making the assumption that what is unexplained about the intercept at the school level is also unrelated to what is unexplained about the slope. And that can be a very tricky assumption to make. And so what happens is you actually get a third term that pops up. So here is the estimate of the variability in the intercept. Here's the estimate of the variability in the slope. And this is the covariance, tau 1, 0, is actually the covariance between the variability in the intercept and the variability in the slope. So it kind of appears because we've introduced a second random term. And so the way we talk about that, so these 2 things are assumed to be multivariate normally distributed. That's what MVN stands for. Both of them with a mean of 0 and known variances here, tau 0, 0 and tau 1, 1, and a known covariance right here that can be estimated, tau 1, 0. So what's interesting is that as you add random effects, things can get quite a bit more complicated. You may also be wondering, so if you look here we introduced a predictor for the intercept, right? Essentially, that's what this level 2 predictor is. It's affecting the intercept. You can also do the same thing, including predictors for slopes. So are there characteristics of the school which cause the average slope to change? And can that be explained? Because you essentially have some unexplained variability here. So you can also include predictors of the slope in any of these equations where you have a random component as well. So each one of these almost becomes like a little mini regression for that particular outcome. So things get pretty complicated pretty quick. Okay, so a further note of caution. Last week, I suggested not to throw all of your predictors into the model at the same time, because you often can't make head from tail and figure out what it exactly is going on. The same problem exists when you have random slopes. And it can be tempting just to say, all right, I'm just going to dump in all the random slopes, all the predictors, and just run it. And there is that temptation to run the fanciest model we can. But again, just like last week, I recommend a slower and more methodical approach. Start with a null model, then add your level 1 predictors, then add your level 2 predictors. And that was all the same as last week. So then test some random slopes. A good place to start would be a variable of interest. So, if you're interested in a variable and that's kind of what you're building your analysis off of, it would be good to know whether or not that variable, the estimate for that variable should vary randomly at the school level or the higher level. And then finally add cross-level interactions, which I'm going to show you how to do in just a minute. But each step of the way, AIC and BIC are your friend. So that is going to be the clue to tell you, okay, should I add random slopes? Should I not? Should I add cross-level interactions? Should I not? And I'm going to be demonstrating how to sort of keep track of those things as you go along and try to make decisions that make sense given the data. So here is a crazier example. So let's say you decide to have 3 random slopes and a random intercept all in the same model. This is actually what you are implying, sort of what's called the implied variance-covariance matrix. You're actually implying that those 4 things, so the random slope or the random intercept, mu0j, and 3 random slopes, are multivariate normally distributed, all with a mean of 0. Here are your known variances, and then you're also estimating 1, 2, 3, 4, 5, 6 covariances. So all of these things need to be estimated by the software, and oftentimes they're very, very small. So that can really introduce quite a bit of complexity into your model and make it really hard to get solid results. So just a little bit of a note of caution. You don't want to go too wild with these. Okay, so I'll just point out before I go on, again, I'm using the Leadership Quarterly data. This might be the last week that we use it, actually. I think I pivot from here to try some other data sets, but I like this one because we stuck with it for a couple weeks and you really learn some of the rules of sort of how to build models and how to increase in complexity, all with the same research question and the same data set. So in this case, I'm including an example output in Stata and R. And this is a model that basically looks like this. This is a random coefficients model from Garson. We have an outcome here, which is hostility. And then we have leadership, T-sig, and GT-sig, which are our level 1 down here and level 2 predictors. And then we have a random variable company ID, which allows to vary at the intercept, which is arrow A. And arrow D, it also is allowing the slope of T-sig to vary randomly as well. So that's just conceptually, that's the model that we're running here when we run the model that I'm going to show you here next. Okay, so this is the Stata output. I actually spend quite a bit of time walking through this on the video, so I'm not going to spend a ton of time here. I'll just note that you now have an additional variance component here. This is the slope of T-sig, or sorry, leadership, not T-sig, it says T-sig here. In this case, we've added a random slope for leadership, and notice it goes right after the colon. Remember I said in weeks past, we want to leave a space there, and that's why, because that's where we introduce random slopes. Notice we still have a fixed effect for leadership, it's over here, but now we've added a random component, and it goes right there. But we also still have our random intercept and our random individual level term. And I have some interpretation of the predictors there and point out some of the other elements here. So it looks pretty similar in R, except R flips the random effects and the fixed effects. So R gives you the random effects first. So we have a random effect here, and we have a random effect here. and we have an individual level effect. So this is the random intercept, this is the random variation in t-sig scores, and this is the random variation at the individual level. And here are our intercepts as well. So it's pretty similar. The one big difference in R, so in Stata, there is an assumption made if you run a default multi-level model that you don't need to estimate what's called a random covariance or correlation between these two things. So that's what's called an independent covariance structure. In Stata, folks, I talk more about this in the Stata video. If you're an R person and you don't use Stata, you don't need to worry about this. Stata R by default includes that random covariance, which is perfectly fine. And so that's what you get by default. So that explains maybe a little bit of the difference that we see in results, but otherwise it's very similar. And again, adding a random slope in place of a 1 up here are, folks. So typically if you want a random intercept, it's 1 and then comp ID. You just put the name of the variable, t-sig. And if you want multiple variables, you just put them in with plus signs. So you could put like lead plus t-sig there, for example, to get 2 random slopes as well. Alrighty, so I think that is it. And the rest of the videos are there, demonstration videos, so hopefully random slopes. So just to recap, this week is all about random slopes. We are talking specifically about how to add random slopes into our models after we have found a model that works pretty well, and how to test for it using p-values or likelihood tests, things like that. And we unpacked a little bit of the notation. So hopefully that makes sense, and good luck.